So let's talk a little more about heat and work. So heat is a transfer of thermal energy between a system and the surroundings, and that is caused by a difference in temperature. So heat is the transfer of thermal energy. Temperature is a measure of the thermal energy within a sample of matter. Heat flows from matter that's got a higher temperature to matter with a lower temperature until they both get to the same temperature, right? So if you imagine, I don't know where these analogies come from, a hot rotisserie chicken from Costco that just popped into my head, and a big block of ice, and you stick them both in the cooler, and you come back, say 6 hours later. What can you predict about the temperatures and what's going on inside the cooler? Is that chicken going to be hot anymore? No. Is that block of ice still going to be a block of ice? Sitting next to a hot chicken? No, it's probably going to melt, right? The chicken is hot. It has more thermal energy, higher temperature. The ice is cold, lower energy, right? Lower thermal energy. So the process that occurs is the heat is going to flow from the chicken into the ice. The ice is going to warm up, the chicken's going to cool down. And that will keep happening until they get to the same temperature, right? So when a system absorbs heat, its temperature changes. Because you put heat into something, it causes the temperature to go up. How much does the temperature go up? Well, that's going to be directly proportional to the amount of heat that you put into it. Put more heat in, the temperature goes up higher. So we can write that as a proportionality. Q is proportional to the change in temperature. More heat, greater change in temperature. Well, proportionalities are nice and all, but equations are better. So we can make this into an equation by putting in a proportionality constant. And that proportionality constant is called the heat capacity. It's got units of joules per degree Celsius or joules per Kelvin, because we have Q with units of joules, and the temperature is in degrees Celsius, and so the units of C would be joules per degree Celsius, and then all the units cancel each other out. So the heat capacity is the amount of heat needed to change the temperature of a system by 1 degree Celsius. Different objects, different types of material have different heat capacities. The larger the heat capacity, the smaller the temperature rise will be. The heat capacity depends on what the matter is, but it also depends on how much matter there is. So heat capacity is an extensive property. Extensive properties depend on the size of your sample. So this reminds me of cooking dinner for the football team. Those boys can eat. So, for a regular family, you've got a little pot of water to make spaghetti, and you boil the water and you make the spaghetti, right? No, for these guys, you need this cauldron of water. And you stick it on a really big burner, and you crank it up as hot as it will go. Which one, the big cauldron or the small pot, is going to take more heat to make the water boil? The big one, right? It took 45 minutes to get the water to boil. Yeah, I made a note of that for next time. 45 minutes. And all that time, heat is being put into the water. So it just makes sense, right? That if you have a larger object, in order to get the temperature to change, you have to put more heat into it, right? So the heat capacity depends on the material, but it also depends on the mass, the size of the sample. So that makes things a little complicated, and so what we use is the specific heat capacity, C sub S, and this is the intrinsic capacity of a substance to absorb heat. Here we've taken the mass relationship out of it, because the heat capacity depends on the amount of matter, it also depends on the type of material. So the definition of specific heat capacity is the amount of heat needed to raise the temperature of particular amount, 1 gram of the substance by 1 degree Celsius. Instead of just the thing, the system, changing the temperature of the system by 1 degree, we're saying changing 1 gram of it by 1 degree. And so that makes the units joules per gram degree Celsius. Sometimes we talk about a molar heat capacity. There it's the amount of heat needed to change the temperature of 1 mole. These are intensive properties. They do not depend on the size of the object. Which leads us to this useful equation. Here it's all spread out and identified. Q equals mc delta T. The delta kind of looks like a capital A, so sometimes they'll say Q equals MCAT. It just seems easier to remember that way. Technically, this is specific heat capacity. We almost never use heat capacity. We almost always use specific heat capacity. So here we have the heat in joules, the mass in grams, the change in temperature in degrees Celsius, and their change in temperature, delta, final minus initial. So it's the final temperature minus the initial temperature. The temperature change may be positive or it may be negative. Positive means the temperature went up. Negative means the temperature went down. And then we have the specific heat capacity. So specific heat capacities will either be given to you in the problem or you'll have the ability to look them up. They are not something that you memorize. So here's a useful table from your textbook. Specific heat capacities of some common substances. Joules per gram degree Celsius is the unit. So here's some different elements, some compounds, ethanol and water, and some different materials, glass, granite, and sand. If you look at the specific heat capacity for water, it is significantly higher than all of the other things here. Water has an unusually high specific heat capacity, which means that in order to change its temperature, you have to put more energy into it than if it was, say, lead or iron or something. That means that water can absorb a lot of heat energy without changing its temperature very much. And this has a big effect on our climate. There's a large amount of water on our planet, right? And the water acts as sort of a buffer to help maintain the temperature and keep it from changing too much. And so we'll see differences in temperature between areas where there's a lot of water and area where there's little water. So if we look at San Francisco, in the summer, San Francisco might be 68 degrees Fahrenheit, where in Fresno it might be 100 degrees Fahrenheit. And we might say, ooh, it's rather cool today. Nice day, right? It's only 100 degrees. You know you're used to the Central Valley when you say it's only 100 degrees today. Why is San Francisco so much cooler? It's only a little bit further north than Fresno. It's because of all the water. San Francisco is surrounded 3 sides by water, the San Francisco Bay and the ocean. So what happens, yes?
Is that why like the school is cold in the middle of the summer?
Yes.
Well, it's not.
Yeah, so the temperature of your swimming pool is not going to match the temperature of the air outside. Because it takes a lot of energy to change the temperature of the swimming pool. So those first few days when it's really hot outside, the water in the pool is cold, right? Towards the end of the summer, when it's been warm, and it's even been warm at night, we always get those like 2 weeks where it doesn't cool down at night, then the water in the pool is significantly warmer, right? So what happens here is, when during the day the sun shines down and it hits things and it heats them up, right? Well, things like metal and concrete, the energy from the sun causes their temperature to change significantly, causes the water temperature to change only a small amount. So the water on the surface of the ocean, on the surface of the bay, warms up a little bit from the sun. Then the sun goes down, and that source of energy, and as I said, source of energy, the projector cut out. That was weird. Now it's back. It's good. Where was I? The sun went down. No more energy coming from the sun. The air gets cooler, right? The bridge, the metal in the bridge, the concrete on the road begin to cool down. And they cool down quickly. They heated up quickly, they cool down quickly. The water heated up slowly, and it also cools down slowly. So now the air is colder than the water, and so the water is going to be transferring heat to the air. And so it acts sort of like a temperature cushion, or like a savings account almost. We can save up some of that energy while the sun's shining, and then when the sun's gone and it's cold, it can send it back out into the air. And so it keeps the temperature of the air from changing as drastically as it does here in Fresno. Here in the summer, it might be 65 degrees overnight and 105 during the day, right? Do we have any large bodies of water? No, we don't. We only have water where there's irrigation, right? So it's very minimal. The air itself is dry. Those days when we do have, you go outside and it's like, ew, it feels like sticky. And those nights when it doesn't cool down, you look at the humidity. It's still not high like it is in the Midwest where I grew up, where 95% humidity happens. Ugh. But it's higher than normal. And the water in the air also holds the heat and releases it back. So arid climates, the temperature change can be very dramatic. That happens in the desert. We are actually in a desert. We're just delusional about it. The desert, it heats up really hot during the day and gets really cold at night. Coastal areas where lots of water heats up a little during the day, cools down a little bit at night. Water is commonly used as a coolant. The coolant in your car is based on water. It's mostly water with some antifreeze to keep it from boiling. Because the water can absorb a lot of heat, take it away from the mechanical parts, because it's good at holding heat and can take it away. Does anybody have any questions? Yeah.
I'm curious about freezing, so I remember we were doing chores with the dogs, and one time, it seemed like if I took cold water outside, it would freeze as fast. If I took hot water outside, it would freeze faster.
Yes. So that's another thing, but that is an interesting phenomenon. So when it's freezing or below freezing outside, we would naturally expect that if you took hot water and cold water out there, that the cold water would freeze before the hot water. And it's actually the reverse. In fact, the last time I was home for Christmas in Minnesota, it got up to minus 12 Fahrenheit. And so we'd heard about this, and we're like, we're going to try it. So we took a pot of boiling water out into the front yard. It was like, now, we're throwing it that way, right? And we'll stand over here. We threw it into the air, It froze before it hit the ground. It's like, what? It has to do with basically a momentum of the energy change. It's very hard to explain.
The more you take energy from it, the quicker it cools.
It's very complicated. I won't even try to explain it, but yeah, that is a thing. Anybody else have any questions?
I figured it'd be nice with the dogs and take more water.
Yeah, and then it freezes faster. So we can do calculations using that Q equals MC delta T equation. So to determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. Okay, before we even get into this, what would be an easier way to figure out if this is gold?
Get a washing pen. Do the old-fashioned.
Well, so it's already been separated from the sand. How do you know if it's gold? Density. Seems to me it'd be a lot easier to measure the density of the stupid rock, but then it wouldn't make a good example for this problem. So this student maybe just wasn't thinking, or maybe she just likes doing things the hard way. She's going to measure its heat capacity. So she weighs the rock and finds it has a mass of 4.7 grams. And then she finds that when it absorbs 57.2 joules of heat, the temperature of the rock goes from 25 degrees Celsius to 57 degrees Celsius. And so what we need to do is find the specific heat capacity of the rock and see if that is the same as the heat capacity of gold. So there's a bunch of numbers here. The first number is 4.7 grams. Well, it says mass of, so that's probably the mass. We'll call that M. 57.2 joules of heat. What's the letter for heat? Q. And then there's two temperatures, 25 degrees Celsius and 57 degrees Celsius. One of those is initial and one's final. What's the initial temperature? 25, right? It goes from 25 to 57. So 57 is the final temperature. The equation that we've been given that involves the specific heat capacity, Q equals MC delta T. So we want to find that's a little too fat. We want to find the specific heat capacity, C sub S. That means we need to know values for the other three variables. Q, we've got that. M, we've got that. Delta T. Well, I've got two T's. I need the change in temperature. Delta T is the final temperature minus the initial temperature. So the final is 57. The initial is 25. And so this is what, 32? Check me on a calculator. My brain is not very good today. So there's delta T. I highly recommend rearranging the equation before you put numbers in, and so we're going to get the specific heat capacity is equal to Q divided by the mass and divided by the change in temperature. I took this equation and divided both sides by M delta T. Now that I've rearranged the equation, I can plug my values in with their units, 57.2 joules. Down here, my mass is 4.7 grams. Change in temperature is 32 degrees Celsius. Do any of those units cancel out? No, they don't. So we're going to end up with units of joules per gram degrees Celsius. But that's okay because those are the units of specific heat capacity. Be careful when you do this on your calculator. 57.2 divided by 4.7 divided by 32. If you really want to multiply there, you have to use parentheses. And 2 sig figs, 0.38. So there's the specific heat capacity. How does that tell us whether this is gold or not? We have to find the specific heat capacity of gold. So we need to go look for it. Oops. There it is. So gold, 0.128. Is this rock gold? No. I mean, it could have gold in it, but it's not pure gold. So, not gold. Any questions? 55-gram aluminum block initially at 27.5 degrees C absorbs 725 joules of heat. What's the final temperature of the aluminum? So I've got 55 grams and I've got 27.5 degrees C and I've got 725 joules. Just pull the numbers out and then we're going to label them. 55 grams, we're in this section where we're using Q equals MC delta T. So kind of having this in the back of our heads, then these are the things we're looking for here. So 55 grams is what? Is that the heat? It's the mass. So I'm going to label this M. Is this delta T? No. That's the initial temperature, right? It's initially at 27. So this is T initial. And then 725, what should I label that? Q. That's the heat. So I want to find the final temperature. If I look at my equation though, final temperature doesn't specifically show up here. So the best thing would be to find the change in temperature. If I know the change in temperature, I've got the initial temperature, I can figure out what the final temperature is. You could do it the other way, but the algebra gets icky and we don't want to go there. What am I missing though? CS, the specific heat capacity. This is aluminum. So I'm going to go look it up. Aluminum, 0.903. C sub S, 0.903 joules per gram degrees Celsius. So if I rearrange that equation, delta T is going to equal Q divided by this other stuff. So Q is 725 joules. Mass is 55.0 grams. Specific heat capacity 0.903 joules per gram degrees Celsius. Do we have some units cancel out here? Yeah, we do. So the joules are going to cancel, and the grams are going to cancel. And I'm going to end up with 1 over degrees Celsius, which is going to give me units of degrees Celsius, which is good because I'm trying to find the temperature. 725 divided by 55 divided by 0.903. $14.597 with 3 significant figures. Is that the answer? No, that's the change in temperature. So now I need to remember that delta T is the final temperature minus the initial temperature. So the final temperature is equal to delta T plus the initial temperature. So 14.597 plus 27.5 . Or 42.1 degrees Celsius. Any questions? We do Q equals MC delta T calculations in Chem 3A, but we typically don't do things like asking you for the final temperature instead of just the change in temperature. So we're just taking it a few steps further.